Good afternoon, everybody. Welcome to SVR305. If you're looking at the name of the session and you're expecting us to play Contra games up here, then I'm sorry, you're in the wrong room. The intent of this talk is to be Lambda cheat codes. Or what are the special things that you could do with Lambda to optimize that last mile of performance that you can get out of your system. A little bit about myself. My name is Vyom Nagrani. I'm manager on the product management team at AWS Lambda. I was here up on stage last year talking about what Lambda is and how you could build applications and different architecture patterns using Lambda. And I'm really excited to see the enthusiasm that you folks have shown in helping us build the feature set for Lambda and building a better ecosystem that you could use. Today we have with us here Rick, the VP for data services, and also the chief data scientist at Hearst, who's going to be sharing some of his experiences of how Hearst technology uses AWS Lambda in their ecosystem. So what to expect from this talk? We'll do a very quick recap of how you could build applications using Lambda, how you could work with Lambda. I don't want to spend too much of time here. I would rather go deep into the best practices. But we'll have Rick come on stage and share what he has built at his company, specifically around the Hearst clickstream and data pipeline, which he'll share more details about. And then we'll do a walkthrough of best practices and hacks and tips and tricks across the entire lifecycle of building a Lambda function, right from development and testing, through deployment and application lifecycle management, through security, scaling, debugging, operations. So we'll do the full walkthrough of what are the things that you as a developer could do to increase the productivity of your own team, to increase what your Lambda function can do, and unlock new use cases. Hopefully, we should leave time for Q&A at the end. Either way, if we'll be at the stage afterwards to take some more questions. So let's get started with working with AWS Lambda. If you have already attended a few sessions here today, then you might have seen some of these slides before, but I'll do a quick walkthrough for those of you who haven't. The way to think of Lambda functions, or the way to work with AWS Lambda, is to think of these three different blocks. There is the input to the Lambda function. So Lambda functions would run every time there is a trigger. There is an event source associated with it. That event source could be different types of events. It could be changes in data state. If you have new data that's coming in and you want to process your Lambda the data on the live, then you can go and build a Lambda function to process that data. You could have data coming in as requests to endpoints. The data could be changes in resource states in your own infrastructure. So that's the input which triggers a Lambda function. The Lambda function itself is a piece of code which you write and upload to the cloud, and we will execute that piece of code for you in response to that trigger. And we have 4 languages which we support today, and hopefully we'll have more languages coming soon. And then the output is what you do with that data. Now, once you have that data, or once you have that trigger coming in, you want to take some action based on it. Lambda can be that compute engine for you, and then you go downstream and either store that data somewhere else after some transformation, or you go and call some endpoint, or you go and take some action based on that input. The benefits that Lambda would give you in this scenario is that it allows you to focus more of your efforts on writing that logic rather than maintaining the whole infrastructure that goes behind that. So you no longer have to go and figure out how many servers do I need to run here? How am I going to scale them? How am I going to go and figure out what the right setup for these instances are? Is the environment the right place? Is the operating system in the right place? All of this infrastructure management goes away. You just have to write the code, and that code will execute in response to the trigger. It also makes it very cost-effective and efficient to run these Lambda functions, to run your code, because you no longer have to maintain a fleet of servers which are waiting there for a request to come in. Lambda is going to only run when there is something to do. So effectively, out of the box, you're getting 100% utilization. And the third thing is bring your own code. Now, as we add more languages, you no longer have to learn any new paradigms. There's no new language to learn, or there's no new frameworks to learn to have to use a Lambda function. You can take an existing code which you have, upload it, and it should work. And then talking of event sources, there are multiple event sources which trigger Lambda functions. And there are different categories which we have put them into, but you can categorize them as you want. There could be data stores which are invoking a Lambda function. There's new data coming in, and that new data is going to be the trigger of the Lambda function. You could have different endpoints that are triggering the Lambda function. If you have something coming in from a voice endpoint or a web or mobile app, request that's coming in could trigger the Lambda function, or even devices who are sending in information about their own state or what's going on in their surroundings could be the trigger to the Lambda function. We have configuration repositories and also event and message services, and this makes up what the infrastructure automation story would look like. So if you have things which are changing in your environment, and those could become the triggers for Lambda functions. And if you can very quickly map what event sources are supported to what use cases you can think of. So we have seen 3 key scenarios that customers are using AWS Lambda for. And this is just a categorization. That doesn't mean that if your workload doesn't fit this scenario, then you shouldn't be using Lambda. This is just the most common ones. As we have data sources as triggers, you could do near real-time data processing. So instead of waiting for data to accumulate and then processing it as a whole batch, just let the data stream in. Every file that gets uploaded, every request that comes in, just treat it as an independent source of data, run a Lambda function against that data, and you can then start processing, generating insights out of that data. And you heard in the announcement today, like FINRA, for example, uses this pattern where they process 500 billion such data points per day using Lambda functions. The other scenario I talked about is these user interactions. Every time there is somebody who is calling into the cloud, who is waiting for a response from the cloud and is trying to take some action based on that user request. And that's where you think of app backends. It's a mobile and web app where you can integrate through API gateway, or it's an IoT device which you can integrate through the AWS IoT, or it's even a chatbot which you can integrate through Amazon Lex, which we announced this morning, or it's even a voice command which is coming through the Amazon Alexa. That also triggers a Lambda function. And the third use case is to build control systems. And this is the infrastructure automation piece. You have changes in your infrastructure. The event source is some other machine in your own setup. It's some other device. It's some other thing which you control as an infrastructure. And you want to create custom workflows. And you want to create your entire application pattern that responds to these changes in state in your environment. And we have customers like Netflix who have built great applications around this space. For example, they have their entire fleet of instances. They are planning to add a layer of management and infrastructure control using Lambda functions, which separate out the application stack from the actual infrastructure by keeping all of this automated. And then we have customers who have tried to do all of these use cases put together. And Hearst is a very good example of that. And we'll have Rick on stage who comes and talks specifically about their data processing application, but he can also share insights on what his vision is on using Lambda in different application use cases. So Rick, I'd like to welcome you on stage.
Thanks, Vyam. Hello. Thanks, Vyam. Hello, Rick McFarland. Quickly, what I'm going to be talking about today is I'm going to share with you a practical example of using Lambdas at Hearst and how we took our clickstream and our old clickstream, which we presented at the last reInvent in 2015, which was a cron-based clickstream, and we, what I called, Lambdafied it. And I'll share with you some tips and tricks along the way if you're planning on doing it at your home. Before I get started on Lambda, quick introduction. How many of you have ever heard of Hearst before? All right. Good. Of those of you that have heard of it, what business is it in? That's the question I usually ask. What business are we in? A lot of people start that, when they answer that, they usually say publishing, but I'm going to try to position a different case for you before I get into the Lambda stuff here on our business and our business model, because that's important to understand why Lambda has helped us achieve better results. So Hearst is a company that owns a lot of different magazines across the world. You might recognize some of these. We have 20 magazines in the US and 300 titles internationally. We have newspapers across the country, so many of our sites collect data or provide information for newspapers. We also have 30 broadcasting stations across the country. And we're also into business-to-business data. Our company owns Fitch Ratings if you're in the financial services business, Black Book in the automotive business, and also a lot of healthcare data. So I would argue that Hearst is more than a publisher. I think that Hearst is really a data creation business. We're in the business of creating data. Our websites, our editors, our properties are creating content that is driving the internet, driving your apps, driving the social media across the globe. So being in the data business, it's important that you have to have a good handle on the big data, because that's where our data is. We're in the petabyte scale size data. And as we all know, big data is a lot different than regular data. It's coming from many different sources. It's unstructured. It's super fast. It's streaming now. It's not in batch mode. And the expertise you need to manipulate and manage this data is quite different. You need cloud engineering and machine learning and people with computer science backgrounds. And underneath it all, the thing that's driving our big data platform at Hearst is what we call the clickstream. And our clickstream is, in our previous presentation, I'm going to show you from last year how it's built and what it's made of, but it's a cron-based clickstream at the beginning of 2016, after the last reInvent. So our clickstream basically collects data from all of the 300 plus websites around the world. We're collecting 100 terabytes of data in a year across all the different properties and streaming it into a Kinesis stream. And then we're performing ETL on it in a Spark cluster. And then we do our data science, where we manipulate the data and create new variables and enrichment on it. And then we pump that into a Dynamo database with an API gateway front end so that we can feed applications and products in real time across the Hearst network. This was our clickstream at the start of 2016. We had about 100 gigabytes of data coming in. The ETL process takes about 30 seconds. We had 100 seconds worth of machine learning and data science performed on it, 5 seconds into the API gateway, and in about 2 minutes, we're able to push data from the front end of our websites all the way through the API backdoor and feed applications across Hearst. Now, the clickstream at the start of 2016 was governed, the process was governed by crons, which are essentially little clocks that manage the throughput of the data, or the shepherds of this process. And they run on 5-minute increments, or at least they used to. You have a cron that runs at the very beginning of the gate, and it then is regulated by a follow-up cron on the Kinesis stream that dumps the data into an ETL process. The ETL shoves it into a data science phase. The data science cron then runs and shoves it into the Dynamo database with an API application on the front end. Well, that was a quick recap of where we were after the last reInvent. And as you know, the big Lambda announcement of the last reInvent got us very intrigued at Hearst. And we met with the AWS team and said we would really like to Lambdify our our clickstream, mainly because the problem with crons is that the speed at which you can transfer data through the process is limited by the clock. And you're not really able to speed it up any faster because the clock has to finish running. In addition, the crons are housed on servers or on EC2 boxes, and those servers need sysadmins and people to manage them. And we were very intrigued by the prospect of Lambdas because it does have the ability to free us up of servers. It's a serverless process. And it also had the promise of being more robust. And also the trigger-based idea, the concept of triggers, made us very excited because we feel like now we don't have to wait for the clock to stop before the next clock runs. We can just let the process dictate its own speed. And so therefore, it's like a bunch of dominoes falling. So I'm going to show you, I'm going to share with you the process over the last year of how we evolved our cron-based clickstream into a Lambda-based clickstream, a trigger-based clickstream. And I'm going to share with you kind of the pains, the growth pains that we had, and some of the tricks and tips that we had that maybe if you're going to do this, will save you a lot of time as you shift possibly your environment to a Lambda-based environment. So this is the core of the clickstream. Really has four main components. The kinesis stream, onboarding the data, the massive amount of data into the stream. You have to process the data, you have to do data science on it, and you have to shove it into an API and store it. So the first thing we wanted to do is the first cron we built was an experimental cron, or the first Lambda we built was an experimental Lambda on the offload of the data from the kinesis stream into S3 for permanent storage. That was a very simple Lambda, and we wanted to start simple and see what we could learn. And so the first thing we built was the kinesis firehose to S3 Lambda, which is triggered by data going into the kinesis stream, and it flows into S3 for permanent storage. And we discovered one of the first little issues about Lambdas is that they have a 5-minute runtime, and if they don't run in 5 minutes, they fail. And we noted that because our next step in the Lambdification of our clickstream is the ETL process. And the ETL process basically takes the data in the clickstream, in the kinesis stream, and pre-processes it, cleans it up, and shoves it back into S3 as well. So we created an ETL Lambda. And the thing we started noticing is every once in a while, the Lambdas would fail because they would take longer than 5 minutes to run. And we noticed that there were some holes in our data. So the first tip I have is that my team decided that we need to actually have a watchdog. So if your process relies on data not having holes and having continuity, one of the tricks that we did was we added a second Lambda that's named almost the exact same name as the main Lambda, and we called it a watchdog. And it's basically a cron-based Lambda that looks to see if there's a failure. And if it is, or if there's a hole in the data, for example, it'll run on its own and fill in the gaps. We call these the watchdog Lambdas. So if you're going to make a production system, I think one of my first recommendations is to think about having a watchdog. And that helps eliminate the need for a sysadmin. 90% of the sysadmin's jobs is to fix holes. And this little watchdog Lambda is pretty cool because it fixes a lot of the holes. So the next Lambda we created was a data science step Lambda that contains some machine learning and some enrichment calculations that we're doing. We're actually translating a lot of our worldwide content into English. And so we have actually a translator in there. And we also noticed that there were holes in there, and so we created a watchdog for that. And then finally, we had a Lambda that actually pushes the data into Dynamo and another Lambda that pushes it into the API gateway, that runs within the API gateway. So one of the things that probably you'll first notice is as you Lambdify a clickstream, you'll probably find that you have a lot of little lambdas, a lot more lambdas than you have crons. And that's basically because you take apart a process due to the 5-minute runtime increments and the watchdog features, and you have to really break it into its very small components and think of them as dominoes. The other tip that we have is in this process, you have to have triggers because you want the process to run like dominoes falling, so when one finishes, the next one starts. And one of the things that John mentioned is the trigger-based mechanism. And one of the things that we did is we have our lambdas writing files back to S3, which are detected by the next lambda and triggers the running of the next lambda in the chain. And one of the tips I have there, for a governance point of view, I started noticing a lot of people using trigger names that are very random all across my S3 resources because everybody started playing with lambdas. And you can't have the same trigger names executing 2 lambdas, so you have to be very careful about the usage of your triggers. And so one of the governance tips I have for you is to try to name your triggers the same name as the lambda and be very precise with the naming of your triggers because you can't have any, you have to be very careful about overlaps in triggering lambdas if you have a lot of people doing lambdas and writing to S3. The next thing I want to talk about is as people started getting comfortable with lambdas, I noticed that my team, everybody was writing lambdas. And I was getting feedback as we were doing this of some of the challenges of writing lambdas. I was trying to find out why people were having problems and what some barriers were. And the thing that really projected lambdas across my organization and made everybody start to use it was the introduction of what we call Lambda frameworks at Hearst. And I'll talk about that for a really quick second here. So the problem with using lambdas to trigger different AWS functions, I don't know if you have ever done that and you use Python as your source code, that's our language of choice. You need a lot of credentials stored somewhere to enable you to take data from S3 and shove it into Redshift or however you're going to do it. You need to have the credentials and modules stored and reusable. And one of the problems was that people would always have to reconfigure these modules and pull them out because they don't come standard in Python 2.7, which is what comes off the shelf on the lambdas. People would always kind of ask me, hey, Rick, what module did you use to do that? Or they'd ask each other on our little network, what module can you use to write from S3 to a server? And we started noticing there's a whole bunch of modules like Botto that allows you to write to S3. If you're going to write a zipped file into S3, you need gzip. PsychoPG is needed if you're going to do anything with Redshift. PGPass is a great library if you're going to store passwords and put them in your code, or you don't want to put your passwords in your code, and so forth and so on. And so we noticed there's a lot of these modules. So one of these guys we had on our team decided, why don't we package all these modules up into one single framework called the Hearst Master Framework. And basically, this is a master environment that we, for all of our Lambda functions, load into S3 or into the Lambda console, and nobody has to actually hunt for all the modules. They're already preloaded into one single framework. And all you got to do is include that framework in the top of your Python code, and you're able to quickly write and do anything you want to with all of the different AWS resources that we have at Hearst. And it's just in one single zip file. And all you have to do is take your Lambda function and stick it into that zip file and push it into the Lambda, and it runs everything. And that had the effect of simplifying the writing of Python code of writing all the code that you could write to make a whole bunch of Lambda functions very easy. And here's a quick example of what we call our Redshift framework. If you're familiar with Python, that's the language of choice that we've chosen. You just have a single line of code in the top of your Python code saying load the frameworks, and that grabs all the PG passes, all the psycho PGs, and all the little Python modules and sticks them in the memory. And you can simply start a Redshift session by simply typing in the host, the port, the database, and the username. You don't need to put your password. You can actually write a query in just one single line of code and use macro variables. You can execute a file in S3. You can you can stick a file in S3 and execute it on a Lambda without having to worry about Botto and configuring Botto. And you can save the data to a JSON object, which if you're going to shove the data into DynamoDB and use it as an API gateway, it really helps to have things in a JSON format. We also made a helpers framework, which if you're familiar with, if you've worked with Botto or any of those things and you want to take data and shove it from S3 into your Lambda environment and then push it back into S3, you need to have, it's kind of a pain to work with some of the Python modules, so we just made a nice simple framework that everybody could follow. And in this example here, it's simply writing a data frame into a CSV. You can download an S3 file, upload an S3 file. You can check and see if a file exists in Redshift or if it exists in S3. I skipped ahead. But I hope you can see, if you're a Python programmer and you've ever tried to do a lot of stuff with the intercommunication of all the different Amazon functions and capabilities, the difficulty of that, having it all wrapped up into a nice, neat little package, if you're going to run a team, has really empowered the team to do a lot more and focus less on the packages and the modules and on just simply writing code and to do things that are actually building products. So let me show you our current, as of today, serverless clickstream. We have the data onboarding off of all 300 websites. We have pulses every 5 seconds coming off of every one of our websites all across the world, dumping into the Kinesis stream, triggering a Lambda that dumps the data into S3 storage. When it sees the little file, it triggers the ETL Lambda, and the ETL Lambda has a lovely little watchdog, a sysadmin kind of following it along every day, and it shoves data into Redshift. We have a data science phase that's doing a lot of stuff, heavy lifting and enrichment in Redshift. We're using actually Google Translate to translate our content in real time as it loads with a Lambda function and shoving that back into S3. That sets off another trigger that offloads that little file into a Dynamo table. And the Dynamo table has an API gateway on top of it. And we're feeding all this data in real time out through the API on the front end. And it's empowering a lot of the new products that Hearst technology is building and connecting the worldwide data into a single console for editors to make decisions at Hearst. So some quick lessons learned. The way our model ran before was a cron-based model. We're kind of limited to a 5-minute window to throughput latency because of the crons. You can't really go outside of a cron's timer. The timer is the limit. And we had infrastructure costs in terms of EC2 boxes and things that we had to pay for. By moving to a Lambda model, we got rid of some EC2 boxes. We reduced our sysadmin costs. We also sped it up so that now the latency is down under 2 minutes. because you're not stuck to a clock. It's dominoes falling, and the faster the trigger happens, the faster the throughput. And I guess there's fewer dollar signs on that bottom one. There's still dollar signs. So finally, I think the Lambda in 2016 has really helped us do a lot more with less in our clickstream. We've really, what I think has optimized our clickstream from 2015 to 2016. You can do things with a lot less of a team. We had sysadmin and a few other folks dedicated to the servers that we have eliminated. Not their position, they've shifted their function to focus more on programming and building products. But we don't need a big team now to monitor these Lambdas if you build the watchdogs smartly. Or you could find one person that knows all this stuff. And anyway, that's my session, my part of the session. So I think I'll ask Bjorn back to start the next section. Thank you.
Thanks, Rick. Yep. So we saw how enterprises like Hearst have started to adopt Lambda in a very serious way. But let's walk through some of the best practices and hacks across the lifecycle of how you can optimize some of these benefits of AWS Lambda. So I'll go through the whole cycle as I talked about, and we'll start with the development and testing. Some of the few quick recaps. When we talk of bring your own code, we support four languages. The resource model for using a Lambda function is very simple. Now, you don't have to go and configure 6 different knobs of how much disk and how much CPU and how much memory and how much I/O you want. There's one single knob. It's called the memory setting because that's the easiest to understand. And that knob goes from 128 MB to 1.5 GB. You just increase that one knob, and you can think of that as the power level of your function. All of the other resources scale automatically according to what that setting is. You can think of how you can use Lambda. We talked about the event sources, but you can think of 2 different invocation modes for AWS Lambda. There is the synchronous, which is you invoke the function will go and execute the code, it will send a response back. Meanwhile, the client is waiting for a response, and it will accept the response from the Lambda function, which is very useful when you're trying to build a web backend, because there's a client out there at the tail end of the browser who's waiting for something from the cloud. And there's the asynchronous mode, which is the fire and forget mode, which is very useful when you're doing data processing. Now, you just upload the data. You don't have to wait for the data to be completely processed before uploading the second piece of data. You keep uploading the data, and it kind of works in that fire and forget mode. And the integration with other AWS services, you don't even have to think of these things. And if it's S3, we know it's data processing, it's going to come in an asynchronous mode. If it's an API gateway, we know it's synchronous, it will come in a synchronous mode. The thing to remember is that Lambda functions are stateless. So you cannot persist anything on the Lambda function itself. Anything which you need to persist should go to some external storage, because there's no affinity to underlying infrastructure. And the reason for that is this allows us to scale out horizontally very, very quickly, because we don't have to gather all the existing state information and then push that out. If there are 1,000 files that you upload, we'll very quickly fan out to 1,000 different copies of the Lambda function and execute all 1,000 together for you. Let's start breaking down the anatomy of the Lambda function. Now, for most of you who have written Lambda functions, these things you must have been through, but I'll do a quick walkthrough. The handler function, you can think of that as the entry point. This is where Lambda function starts execution of your function. Anything you write outside the handler function in Lambda will be executed once when the function starts the very first time. And then we will see that after that, only the parts inside the handler is executed. So you can start using some global variables and global namespaces you can define outside the handler function. The request that comes in, whether it's a direct API call request in which whatever your header is, or it's some event source which is triggering the function, the entire request will come as an object that your handler function is supposed to accept, and that's called the event object. So we have predefined objects, the object formats for all existing AWS events and integrations. And remember, these objects are normally typed JSON, but if you're using simple data types are also allowed. So if you are doing something if all you want to pass is an integer, then you can do that. But you also can pass POJOs and POCOs for Java and C# respectively. The context object is something which people quite often don't use, but it has a lot of very important properties and methods which you can make use of to optimize some of the functions settings. For example, Lambda has a max timeout of 5 minutes, but you can see inside your function how much time is left in current execution before this function is going to time out. And you can start taking actions based on how much time is left for your function. You just have to call the get remaining time in milliseconds object, the method, and you can get that inside your code. Similarly, you have things like the AWS request ID. Now, you are trying to build idempotent functions. Anytime you're trying to build code, one thing to keep in mind is that you want idempotency. Lambda is designed to be an at least once delivery service. So if you're handling objects, you want to make sure you're not processing the same file again. You want to make sure you're not processing the same transaction twice and charging your customer twice, or even double counting your data. You can use the AWS request ID as that unique identifier of this is the request ID that Lambda got for this data, for this piece of data. You can also get things like the invoked function on. What function is currently running? Like, let's say you want to share the same piece of code across hundreds of functions. Your code needs to know which function do I belong to, which function am I currently running, and you can get that as an invoked function on property inside the Lambda function. So you can look up a lot of these different properties. I'd recommend to go and look at the context object, see which are the things which you can use. There are lots of interesting stuff in there which might be able to help you optimize. The other thing is the function metadata. So we talked about the function itself. Now look at what the metadata of the function is. And there are 3 objects which I'd like to call out. Everything else is a standard name, description, size, the code size, the code SHA. All of those are important things, but the 3 I'd like to call out is the VPC config. The VPC config allows you to specify which VPC you want your Lambda function to be able to access. Lambda functions, when they run as a default mode, they do run inside a VPC. It's just as our VPC. So this is not a security feature. This is more of a access to my VPC feature. So when you set this up, you will be able to connect to the VPC and then access the private resources in a very secured manner that only you will be able to access and nobody else can. And when you set this, Lambda will set up an ENI. It will take an ENI from your account. It will take a private IP from the subnet you provided, and then connect into your VPC to access these resources. Another thing we announced this morning is the dead letter config. What the dead letter config can do is, as Rick mentioned, an important thing is to make sure that when the Lambda function fails, you want to make sure the data isn't lost. So this is available in the asynchronous mode today, where you can specify an SNS topic or an SQS queue as a dead letter queue for your Lambda function. And then when Lambda tries to execute the function and it cannot, it'll write that event message onto the dead letter queue, which will allow you to then redrive those messages in the way you want. So now you have that the durability of your data, that it's either going to get processed or it's going to be returned back to me in the dead letter queue, which I can redrive on my own. And the new one that we announced a couple of weeks ago is the environment variable. This allows you to pass custom key value pairs as part of configuration. So you can add things like, if you want to reuse the code across different stages, then you can add things like, well, this function is my test function. So it needs to access a certain list of checkpoints or a certain list of endpoints that it's going to talk to. So all of those parameters can go as your environment variable. Or even if you want to add things like your logging level, you can run the same function either in the prod mode or in the debug mode. And what you log inside the function depends on what environment you pass in here. And note that environment variables are encrypted with the KMS key that you specify. So these variables are going to be encrypted at rest when, on the function. A couple of limits to keep in mind. I'm not going to walk through all of the limits, but the thing to know is that there are certain limits on what are the types of things you can and cannot pass to the function. So it's always good to know what these limits are. For example, when you're doing a function invocation, in a given request, you cannot pass more than 6 megabytes of data. A given function size cannot be more than 50 megabytes, and this allows us to maintain the whole latency of invoking the Lambda functions. The thing I want to call out is that some limits are flexible. We have a default throttle limit, which gives you an ability to safeguard against a runaway function. And this is a soft limit. If you want Lambda to scale, if you know that your function is set up in a mode where it's not going to be accidentally run away, this is in an environment where nobody can touch, then you can create a support ticket, and we'll increase this limit for you. Also to think about is what happens behind the scenes, what is a Lambda function? And I'd like to talk of the container model for it. That a Lambda function effectively is a Linux container running on Amazon Linux. And we try to reuse this container as many times as possible. For the first time you call the function, we'll create this container. We'll do all that scaling for you. It's all AWS infrastructure in AWS management. You don't have to worry about container management at all. But what does happen is that the containers get reused so that we can get better and faster responses as more data needs to be processed. And you can actually make use of this container reuse policy. Anything which you write to the /temp will be available if you end up on the same container the next time. How do you use it? You can set up some things like a local cache right there inside your Lambda function. Anything which you write to a global namespace in memory is going to be there. So you can start adding things. If you have to pull down configuration, if you have to pull down some special libraries, just pull them down once into your code in the init or outside the handler function, and then that stays in the container as long as that container runs. And we've heard a lot about cold start, so I want to touch upon that a little bit. A cold start effectively is a time taken for us to start a new container. And you will see the occasional cold starts when Lambda is scaling up on your behalf. The way to think of these cold starts is, if I'm scaling up, then there's a new container which needs to be created, and that's the time it takes. But there are a couple of ways in which you can reduce these cold starts. So first, as I said, there's one lever. More memory means more power to the function to execute. So the more memory you allocate, the faster we'll be able to load the function. That might reduce your cold start. And oftentimes, more memory might not necessarily mean more money, even if the pricing is in terms of GB seconds. If you're increasing the GB, but the faster memory is going to make you consume fewer seconds, you might end up paying the same thing, but getting the results faster. Smaller zip files will also mean that there's less of stuff to load. If you don't package all of your libraries for every code, but you only customize what libraries you need, and there are tools for shrinking the size of your zip. And you can just package all the libraries you need, and that's going to take less time for Lambda to load. And then there are some language properties. There are some runtime properties. Node and Python, interpreted languages like Node and Python start faster than compiled languages like Java and C#, because we don't have to boot a whole JVM or boot the whole .NET Core framework. So if you have an application which is cold start, where you cannot handle any cold starts, then you might consider using a language which doesn't have that problem. The other thing to think of is the execution environment. Where does a Lambda function run? And again, I'll not go through the specifics of each item. The thing to remember is that behind the scenes, it's an Amazon Linux AMI. So anything which you can compile against this Amazon Linux AMI and include in your zip file can be run as a Lambda function. You just have to add a wrapper in one of the known languages that forks out to that process. And remember that all of these things keep changing, whether it's the underlying OS or it's the libraries which we include as a default. All of these will change over time. Behind the scenes, what otherwise you would have to do if you're managing your own infrastructure, here Lambda is doing for you. We will keep updating the libraries. We will keep moving to the newer versions as things comes out for the SDKs, for the runtime languages. So what you should do is you just keep a note. I have a link in here. You'll be able to get it when the slides are published, and go and look at what the current supported versions are and keep yourself updated inside the code. But if you do need a specific library, you can always include it as part of the zip file. Like that, you can override that library and you say, I want to use a specific version of the SDK because I have some dependencies on it. So that's about development and testing. So now let's look a little bit about the deployment and ALM. When you build a deployment package, effectively what you're doing is an independent set of code and libraries which the Lambda function can execute without anything and having to call out to anything else. You can still make outbound API calls, but you need to have all the code which you are bringing in. So with Node.js and Python, it's kind of easy. You can start do an npm or pip of all of these libraries, install everything into one zip folder, and upload it, and we'll run the whole thing. With Java, you can do the same thing. You can upload a zip or a jar. But the benefit of Java is you can use the existing IDE plugins like Mavens and Eclipse. And you can include not just the compiled class files, but also all the required jars into that lib directory, and we'll include everything when we are running the Lambda function. Same thing with C# that we announced this morning. You can include a zip file, or you can bring in a standalone DLL. But with C#, what most developers are used to is the Visual Studio, and we have provided the full integration for an end-to-end package and deploy right inside of Visual Studio. So from Visual Studio, you don't have to worry about the packaging. You don't have to worry about which library I need to call. You just declare the libraries, and Visual Studio, when it does the package, it'll include all the NuGet packages automatically and deploy it, including all the platform-specific libraries automatically managed by the Visual Studio plugins. The other thing to think of is managing continuous delivery. We had a session not long ago in this track, which you can go and look at later, which talks of how you could set up a continuous delivery pipeline for your Lambda functions. So the standard way of what we recommend is to have a code commit as the source of your repo. Code build is a new service which we launched this morning, which will allow you to take your existing code, all of your existing libraries, and create a complete zip file which has the build version of which does the npm and pip install, which does the Java compilation and the program for you. And then you can set up a code pipeline that gets triggered every time there's a change in the code commit repo, so that this becomes an automated end-to-end repository where your code commit is a reflection of all of your Lambda functions. The moment you update a new one, it kind of gets through the whole pipeline, and it'll deploy it as a Lambda function. But those are the AWS tools. Now, you have lots of other tools which you could use too, like they are open source. You can have a GitHub if you're using GitHub as your code source. You could still use code build and code pipeline, or you could start looking at other third-party frameworks such as Jenkins. And we have a Jenkins plugin which will allow you to do the build and test. And there are lots of partners who we are working with, such as CodeShip, who can do that final deploy for a Lambda function. We also have the AWS serverless application model, which you can use in this space. Similarly, you can start building your own thing as well if you want. You can use Amazon S3 as a source and use Lambda functions to do all of these steps. Like all of these steps at the end of the day is just new compute which you need to run. You can run them as Lambda functions. In terms of tools and frameworks, we have lots of tools which we'd like to talk about. The CloudFormation announced the new AWS serverless application model, or AWS SAM, which provides new serverless resources such as APIs, functions, and tables in an open specification, which allows you to very easily and quickly deploy Lambda functions and deploy the whole serverless stack. Chalice is another AWS framework which works the same thing, which is a Python microservices framework. And you can quickly create and deploy applications using that framework. Or there are third-party tools which have actually provided a lot of value to our customers on how they can package and build these Lambda functions. When you're, again, deploying the Lambda functions, you need to think about function versioning and aliases. Remember, a version is an immutable copy of code plus configuration. So you can either keep developing the function and keep updating the $latest. So you can say my function $latest and just keep updating that. Or you can actually go and say, I want to publish a version. I want to create a snapshot of the state of things as of now. And it'll automatically create something called my function :1. And then that becomes a frozen snapshot, which no longer has to change. You can continue iterating on $latest. And you can publish the second version whenever you need to. Also, you could set up aliases, which allow you to point to a specific version of the Lambda function. And you can go in and say, my function :prod is the alias that I want to point to, so that my client code always just points to this one function, one alias. And then behind the scenes, I can point that alias to any version number that I want. So moving to security and scaling, Lambda has these two modes in which you would run. Most of the cases, there is going to be this external trigger which invokes the Lambda function, which we'd like to call the push model. So here, we make it easier by allowing you to specify a resource policy. A resource policy allows you to grant permissions to the downstream resource to be able to. You grant a permission to your Lambda function that determines which service will be able to invoke it. So you have a resource policy to Lambda that says, allow me to be invoked by S3 puts. And the other side of it is a pull model. If you're reading data off of Kinesis or from DynamoDB streams, then Lambda is actually reaching out and trying to fetch the data from these two streams. So there, you have to give an IAM role to the Lambda function that says, allow this function to go and read off of a downstream resource. So just make sure you're aware of those two different modes. The other thing to think about is throttling. So what is a concurrent execution and what is throttling? So concurrent executions are effectively how many parallel copies of Lambda are running right now. And that's what we throttle based on. So the way to think of it is if I have X number of requests per second, and each request is taking Y seconds to execute, then on an average, at a given point in time, I have X times Y functions running on my code. So what happens when you do get throttled? Because that's a throttle limit. That's a limit of 100 as a default, and you can get that increased. What happens if you do get throttled? For stream-based services, for Kinesis and DynamoDB, if you do get throttled, if you happen to do get throttled, you forget to raise your limits, it gets automatically retried. You don't even have to worry about it. It just means that it'll be a little bit of while before we can get to your function again. For asynchronous invocations, we will keep retrying throttled invocations for up to 6 hours. So this allows you to send in a huge burst of data, way higher than what your limits are on concurrent executions, because now you want to protect your function against runaway. And let Lambda get throttled. Even if it does get throttled, it just means that behind the scenes, there's this queue which is backing up. And then Lambda will slowly process through that queue at the rate that your concurrent executions allow. And for synchronous invocations, a throttle, because we don't know, it's a client waiting there. Like we can't keep retrying when the client has submitted a GET request, and we can't keep retrying in the back end. So we send a 429, and we let the client decide what it wants to do. We do recommend that the client can put in, even if it's a client browser SDK, put in a few automated retry inside the SDK, and we'll retry that for you from there. Other things to think about when scaling. For Lambda itself, as we talked about, a throttle is not an error. In most cases, if you do get throttled, then that just means that your processing is delayed by a few seconds. The moment the queue gets it's emptied, you're going to be executing in real time again. So it's OK to get throttled. But if you do that, you see that you're continuously getting throttled and you're always falling behind, then you can submit a limit increase request, and we'll increase that limit for you. And therefore, if you expect these sudden spikes in invocations, then you can consider asynchronous invocations. You can consider that fire and forget mode, especially if you are not trying to get data from the cloud. In get data, you have to be asynchronous. But if you're just putting data onto the cloud, if you have somebody feeding data into you, use the asynchronous mode. So that way, even if you do get throttled, you don't really have to worry too much about it. And if you're expecting a huge limit increase, then always reach out to AWS support. The other thing to think about is upstream and downstream services. Lambda is designed to scale out horizontally very, very quickly. We respond oftentimes in low 2-digit milliseconds, is that the type of responses customers have told us that they're getting. That might not be the type of responses which all of your systems are designed for. So you have to remember that you have to build in this retry logic. You have to build in the client application, the back-off logic, not just in your upstream, in the function that's invoking the Lambda, but also in the Lambda itself. It has to be sure that inside the code, you sometimes have to retry. You have to do some sort of back-off. Because if you're talking to something which doesn't scale horizontally, like a relational database table, or you're calling an internal endpoint, which is used only to a few transactions per second, then that might not scale to the same limits of Lambda. And you always should try to limit your concurrency, therefore, when you're talking to relational databases. The last thing I want to talk about is debugging and what you would do in that case. So let's talk about errors. So what are the type of errors that you could get? So if the function executes in the right way, you will get a 2xx type of response, a 200 or a 202 response. But if it fails, you could either see a 4xx client error, which oftentimes can be fixed by the developer. These are often things like, well, you're trying to invoke a function which doesn't exist, or the request payload is larger than 6 MB, and therefore I can't process it. Or you could get a 5xx error, which could be fixed by your admin, but in some cases you might need to reach out to AWS support for that. But most of these errors are around EC2 ENI management when you are running inside the VPC mode. So what's the retry policy there? So we saw for throttles, we'll continue to retry. But if there's an error for stream-based services, we do the exact same thing. We continue to retry, because there we cannot skip over data. For asynchronous invocations, what we do is we'll retry 2 extra times. After that, we'll write to a DLQ. And similarly, for synchronous invocations, we'll let the client decide. It's up to you what you want to do. For tracking and tracing, the other thing you could do is we have an upcoming integration with X-ray, which is going to allow you to look inside of your function, to look inside not just the upstream function, not just the Lambda function, not just a downstream, but a complete picture of what's going on inside of your function and inside your entire setup, and where each request is taking how much of time. The other thing which is available today is an integration with CloudTrail. Every request is going to be integrated with CloudTrail. So all the requests, all control plane APIs are going to be tracked. So the invoke API, for example, might not be tracked, but everything else which is going to be creating a function, if you see some sort of errors on your function, if you see any new functions created or any objects which are anybody's changing your function code, all of those will be logged to CloudTrail, and you can see you can start debugging what's going on there. For normal troubleshooting and monitoring, we have everything goes to CloudWatch logs and CloudWatch metrics. We have a default log system where we have a start, an end, and a report as a default log which goes in. Plus, inside the function, depending on the runtime, we have different ways in which you can submit the logs. For Node, for example, it's console.log. For C#, it's lambda-logger.log. So you find out what the right method for calling is. Anything which you annotate with that is going to go inside CloudWatch logs too. And metrics, we have a few default metrics which we give out, such as in number of invocations that you are running, the duration, average duration of invocations, if there's any throttles or any errors. Those are all default metrics that you get out of the box. But remember, you can build your own additional metrics. And the Lambda function, the benefit is that it's your code. How difficult is it to write the code for publishing to CloudWatch metrics? It's one line of code. It's one API you call on CloudWatch metrics. So start publishing your own metric, such as things like your business-centric metrics. So these are all operational metrics, but you can start submitting things if you're getting, for example, requests from different clients. You can, every time you find a unique client ID coming in from the request, you can say, well, this is a new customer I served. So you can have your own metric of customers served today, which Lambda never knows, but your code does. Also, you can go inside your logs, and you can create filters that will automatically deploy your different tags as metrics. So hopefully that gave you some value. The key takeaway I want to get out of this session is that Lambda has now become a core component of the AWS serverless platform. Now, over the last years, what we have seen is multiple different features and environments have been, the whole support system has been increased to make Lambda be part of your production systems. We do recommend to stay in touch with us with on the Compute blog, or check our detail pages, Lambda forums. All are good ways of getting in touch with us. Since we're out of time on stage, I'll do Q&A at the side, but hope you had a good time, and do request remember to complete your evaluations. Go through some other sessions. See you at the replay party.